Okay, so as Malte said, this is joint work with Jonsson and Thomas in Köping. So in this talk I'm going to introduce the problem, then tell you a bit about our contribution, and then finally conclude. So as many of you know, the causal graph is widely used in planning to capture the interdependence that exists between different variables of the problem. And of particular interest has been the case where the causal graph is acyclic. So an acyclic causal graph means that many of the sub-problems that you might encounter, such as setting the value of some variable to a specific value, become independent of one another, because when you're setting the value of a variable, you can ignore all variables that you don't directly or indirectly depend on. So there are several examples of research exploiting the fact that the causal graph is acyclic. So a couple of examples are decomposing planning instances into sub-problems, and Malte derived this causal graph heuristic. And so the question we want to ask here is whether planning is easier when the causal graph is acyclic or not. So I'm going to make this question, in the next couple of slides I'm going to try to formulate this question in a more formal way. So I assume most of you are familiar with planning. So we studied the typical planning problem where you have a set of variables, a set of actions, an initial state and a goal state. We're going to look at both strict planning where the variables are binary, and the extension which is called SAS plus planning where variables can have multiple values. And you're interested in, of course, in fact, so we're doing classical planning, we're interested in just finding a sequence of actions from the initial state to the goal state. So, to formulate our question, first, the causal graph then is a graph where you have one node per variable. There's an edge between two variables if there's some action such that the first variable appears either in the pre or post condition of the action, and the second variable appears in the post condition. So this is an example where the causal graph is acyclic for some problem. And the fact that the causal graph is acyclic implies that actions are unary, because if there are two more variables in the post condition, that will already induce loops in the causal graph. Okay, so we're going to use tools from complexity to formulate our question about how hard it is to plan for these problems. So we're going to study the following two decision problems. First, the problem of plan existence, which says that given that you have some planning instance, does there exist a plan solving this instance? And the problem of bounded plan existence, which is the same, but now you have an upper bound on the length of the plan that the plan has to have. And it's known that both of these problems are p-space complete, both for strict planning and for SAS plus planning. And if you now restrict these problems, or you define these problems for planning problems with a cyclic causal graph. So we define this plan existence with a sig within parentheses, which now represents plan existence when the planning instance is restricted to have a cyclic causal graph. And the same for bounded plan existence. Well, what's known about the complexity of these problems? Well, in fact, many researchers in the literature for different kinds of restrictions on planning problems have shown that these two problems are NP hard. So our question now becomes, well, what's the worst case complexity of these two problems? And in fact, looking at the literature, this is not clear because there's a gap here. We have a lower bound which says that they are NP hard and an upper bound which says that they are p-space, but it's not clear what the exact complexity class is. And that's what we're going to look at in this paper. And actually, I'm going to give a spoiler already here and tell you what the results that we found are. Well, we found that the problem of plan existence for strict planning with negative preconditions is p-space complete. And as a corollary, because the other problems are harder, then both plan existence and bounded plan existence are p-space complete, both for strict and SAS plus planning, under the condition that strict planning has negative preconditions. And we also show a second result. We study a subclass of SAS plus planning with a cyclic causal graph and strongly connected the main transition graphs. And in this case, plan existence is easy. It can be done in polynomial time, while bounded plan existence is hard. Okay, so I once was at a talk by Richard Korf, who I don't know if he came to this session, but he said, if you're not interested in the details, now's a good time to fall asleep. I'm going to, in what follows of what remains of the talk, I'm going to try to give you some understanding of how we arrived at these results. So, when showing a complexity result in general, that something is X-complete, or P-space complete in this case, we have to first show that it's membership, that the problem is in this complexity class. Well, trivially for plan existence for a cyclic causal class is trivially in P-space, because plan existence for general strips is in P-space. So what we have to do is show that plan existence is P-space hard. And we're going to do this by reduction from a known P-space complete problem, namely QBF SAT. So QBF SAT is the decision problem that you have a Boolean formula F, which is where phi is a SAT formula, and each variable is quantified either by universal or existential quantifiers. So the question is whether this formula is satisfiable or not. So this is a known P-space complete problem. And what we have to do to show P-space completeness for our class is that for each QBF, we have to construct in polynomial time a corresponding strips planning instance with a cyclic causal graph, which is solvable if and only if F is satisfiable. So I'm going to, before showing what our planning problem looks like, I'm just going to describe a general algorithm for solving QBF SAT. So if you're given a partial assignment to the I-1 first variable, you can define a partial QBF, where in the SAT formula phi you replace all the I-1 first variables with their value in the truth assignment you have, and you keep the quantifiers on the remaining variables. So Qi here is either a universal or existential quantifier. And there's now a recursive relation on these partial QBFs. Namely, if Qi is a universal quantifier, then the QBF Fi, given this assignment, is satisfiable if and only if the QBF on Fi plus 1 with the same assignment and Xi true is satisfiable, and the same assignment and Xi false. And if Qi is existential, the same thing holds, but now only one or the other has to be satisfied. So an algorithm for solving QBF SAT is given by, you iterate over all possible truth assignments to the variables of the QBF. You record whether each of these partial QBFs are satisfiable. And the original formula F is given by the QBF F1, where the assignment is in fact empty because there are no variables before x1. And you can do this in polynomial space, because once you've used this recursive relationship to determine the satisfiability of Fy, you can throw the other two away. You don't have to keep them around, although they're exponential in any of these partial QBFs. So what we're going to do is we're going to try to construct a strips planning instance with a cyclic causal graph that simulates this process. And in fact, the hardest part of doing this was to have the correct way to iterate over the assignments. So there are counters in the literature that iterate over all possible assignments and that have a cyclic causal graphs. But the problem when you have plan existence is you don't want to be able to count down again. You have to ensure that you only iterate exactly once over each variable assignment, because otherwise you can count down and flip something again. And we have to ensure that our planning instance is satisfiable if and only if the formula is satisfiable. So we had to invent a new way of simulating loops. So I'm going to try to show you this new way of iterating loops is in fact based on a very small planning instance that I'm going to try to illustrate. So it's an instance that has 5 variables, a, b, x, u1, u2, all binary. They're all false in the initial state, and the goal is to make u2 true. And there are 6 actions. So to make u2 true, you have to apply the last action. So u2 1. This one has u1 as precondition, so you also have to make u1 true, which is possible in the initial state. But the second action also has x as a precondition, so you have to apply the action that says x to true. That requires b as a precondition, so you have to set b to true. The last action requires not b as a precondition, so you have to reset b to false, and to do that you have to set a to true. So the plan will look like this. And this also, the causal graph of this problem is acyclic, which is easy to show. And the plan for this problem is in fact very restricted. So the only change you can make to the plan I showed you is to switch x1 and actions x1 and a1. So in particular, you can guarantee that x, which x is the variable whose value you want to iterate over, you can guarantee that it's always false before the first action and always true after the last action. So now what you can do is you can add additional actions and additional preconditions on these actions, and you not guarantee that x is false whenever you apply these first actions, and x is always true whenever you apply these last actions. And you can have a nested loop by now putting in a similar planning problem between u0 and u1 here. So I'm not going to illustrate exactly what the planning problem looks like, but this is what the causal graph looks like. So the top row and the bottom row is an exact instance of the planning problem I just showed you. And then nested within those are other similar planning problems that iterate over the other variables. And in the middle, there's these S1, S2, etc. to T, whose job is to check whether the SAT formula phi is satisfied given the current assignment to the variables of the formula. And there's an extra mechanism here that you can see on UN0. It branches into it has two branches, whose job is to check whether the corresponding partial QPF is satisfied or not. Okay, so, and there are edges missing here, but putting those edges in would make the graph look too messy, so we've taken them out. But you can verify that this causal graph is in fact acyclic. And that there's a solution to this if and only if the formula is satisfied. Okay, so that concludes the first result. So the second result is on this restricted domain where the variables have strongly connected domain transition graphs. So the domain transition graph illustrates possible transition between the values of an individual variable. And the fact that they are strongly connected means you can reach any value from any other value, although the preconditions might not always be satisfied. So we define this subclass of SAS class with a cyclic causal graph and the strongly connected domain transition graphs. And we show that plan existence is in P for this problem, while bounded plan existence is hard for a complexity class which is called sharp P, which I'll talk a bit more in a second. So to show that this problem is in P, it turns out in fact that all planning instances in this class have a solution. So the proof is by induction on the number of variables of the problem. So to prove plan existence, all you have to do is to verify that this property holds, and this can be done in polynomial time, so plan existence is easy. To show that the bounded plan existence is hard for this complexity class, we can have to reduce a known complete problem for this class to our class. This sharp P is a count, so instead of having a decision problem, this sharp P class, if you're not familiar with it, is defined on counting, what's known as counting problems. So the problem we reduce from here is called at least unsat. And it's formulated as follows. So given a 3-sat formula f and an integer k, is this formula unsatisfied by at least k variable assignments, distinct variable assignments? And we now reduce this to a problem of our class in polynomial time by constructing in polynomial time a planning instance in our class that has a solution of length at most some function of the formula and the bound, okay, if and only if f is satisfiable. Okay, so again, I'm going to try to give you an intuition of how this reduction works, but not present the full reduction. So the idea here is to maintain two gray counters, essentially V and C. V, the counter V, represents the current assignment to the variables of the formula. And the counter C counts the number of assignments that we've seen so far that are unsatisfied. So gray counters, like I mentioned before, can count both up and down. And also we need an additional variable S that is the only one. All the other variables are binary. All the V and C variables are binary. But we need one variable whose domain is larger than 2. So it has domain where the values are of type V or C as well. And the transitions are only possible from V variables to C from V values to C values and vice versa. And changing the value of some variable of type V or C has a precondition on S, corresponding precondition on S. So the idea here is to choose this function G. So we choose this function G in a way that, and the goal state. So the goal state is you have to count through all the variables, all the variable assignments. And the goal state on C is defined such that you have to find exactly K unsatisfying assignments. And we select a bound based on the formula in this K, such that you can only you can only reach the goal within this bound if you never count down. So as I mentioned before, gray counters allow you to count down as well as up. But you can, when you do bounded plan existence, you can avoid the problem of counting down by setting a tight bound that makes it impossible for the plan to be of the appropriate length if it counts down. This ensures that the plan cannot cheat and count an unsatisfying assignment twice. Okay, so the causal graph for this problem is also a bit messy. So it has the two counters, where the C counters depend on the value of the current variable assignment, and both counters depend on the current value of S. But again, you can check that the causal graph is in fact acyclic. So that's really the end. So the conclusion is, well, in the worst case, in fact, you cannot guarantee that planning is easier, even when the causal graph is acyclic, with the exception of strict planning with positive preconditions. So the reviewers asked us, do you really think that there's no point then in studying planning problems with a cyclic causal graph? Well, we probably think that there is a point, because they do appear simpler in many practical examples. So we do still think that it's worth looking at problems with a cyclic causal graph. It's just that in the worst case, you cannot guarantee that planning is easier. And additional restrictions are necessary to guarantee a better worst case complexity. So one thing it might be interesting to look at is restrictions such that planning is hard in general, but easy when the causal graph is acyclic. In fact, one such example is strips with positive preconditions, which Bylander did not explicitly talk about the causal graph, but he showed results for what is essentially strict planning with positive preconditions and the cyclic causal graphs that show that they are bound away from P-space. So they are easier, but hard when there's no restriction on the causal graph. Okay, so that's it.
Thank you.